Good afternoon, and thank you for joining us for today's webinar. Today's webinar is the first in our DNA kinship series. DNA kinship tests are proposed as a method within the Department of Homeland Security for confirming the presence of a biological relationship between two individuals for immigration purposes, preventing human trafficking, and identifying mass disaster victims. This webinar series discusses the findings from research conducted at George Washington University to offer improvements on kinship testing methodologies. This research was supported by the DHS Science and Technology Directorate. Today's talk and today's webinar topic is a cost-benefit analysis of kinship testing involving full siblings and half-siblings. Your subject matter expert and presenter for today is Brandy Iorio. She is currently pursuing her Master's of Forensic Science in Forensic Molecular Biology at the George Washington University and is expected to graduate in spring 2018. She received her bachelor's degree in biology and psychology from the University of Virginia in 2015. She currently works at the District of Columbia Department of Forensic Sciences and conducts research for the Department of Homeland Security Science and Technology Directorate in collaboration with SNA International. Her current research focuses on kinship testing with siblings, which investigates the effects of using additional siblings and substituting half-siblings for full siblings in kinship tests. Our quick disclaimer: the opinions, findings, and conclusions or recommendations expressed in this presentation are those of the presenter and do not necessarily reflect those of the Department of Justice. Any products and manufacturers discussed are presented for informational purposes only and do not constitute product approval or endorsement by the U.S. Department of Justice. And without any further ado, I would like to go ahead and hand things over to our presenter today, Miss Brandy Iorio.
Good afternoon, and thank you for joining me for my webinar today. My name is Brandy Iorio, and I will be discussing a cost-benefit analysis of kinship testing involving full siblings and half-siblings. There were a number of contributors from both the George Washington University and SNA International throughout the course of this research project. These contributors included Timothy Graham, Ria Tekti, Rachel Holderly, Daniele Padini, and Moses Shanfield from the George Washington University, and Breanne Knight and Amanda Sozer from SNA International. As a disclaimer, the authors of this study have no conflicts of interest to declare. As a disclosure, this research was funded by the Department of Homeland Security Science and Technology Directorate. The contract number is provided below. For this particular study, this research is involved in a four-part study conducted at the George Washington University on kinship analysis. Different methodologies involving the testing of full siblings and half-siblings for kinship purposes were examined for their effectiveness and practical applicability in agency labs. One of the major objectives of this research was to provide recommendations to enhance future methodologies of the Department of Homeland Security. First off, I'd like to start off with an introduction on kinship tests. So a DNA kinship test is a method for confirming the presence of a biological relationship between two individuals. DNA kinship tests assess the relatedness between two or more individuals for a variety of purposes, including parentage testing, forensic casework, identification of victims of mass disasters, and immigration. DNA testing is a frequently utilized tool of verification for family reunification purposes, since individuals abroad have the right to join relatives who are citizens of another country. While applicants must submit official documentation, such as birth or marriage certificates, to establish identity and relatedness to another individual, DNA testing can be employed if those documents are unable to be located or if the authenticity of such documents is unsure. For these purposes, DNA tests can provide proof of the alleged biological relationship. And now we will start a poll for our audience and ask a question and have you all participate and provide an answer for us. This question is how frequently do you test relationships in your lab? 1 to 10 times per year, 10 to 100 times per year, more than 100 times per year, or I don't conduct relationship testing. And as we can see, it seems that a lot of our viewers do not conduct relationship testing at all. 50% do not, 10% to 11% test relationships 1 to 10 times per year, about 25% test relationships 10 to 100 times per year, and about 15% test relationships more than 100 times per year. Now, what happens when a closer genetic relative, such as a mother or father, is unavailable for kinship testing? Well, full siblings and half-siblings can be used instead to establish the biological relationship in question. And now we will ask a second question for the audience. And this question will be, if you test relationships, how frequently do you test siblings in your lab? 1 to 5 times per year, 5 to 15 times per year, more than 15 times per year, or I don't currently but plan to in the future. And it looks like, so far, about 34% don't currently but plan to in the future, 31% test siblings more than 15 times per year, 15% say 5 to 15 times per year, and approximately 18% test siblings 1 to 5 times per year. Well, hopefully for those who are planning to test siblings in the future, hopefully this information is extremely helpful for you. Now, in regards to the testing of siblings in kinship testing can be quite complicated since the levels of DNA shared between siblings can vary significantly. For example, full siblings can share 0 to 100% of their DNA from 2 shared parents. Typically, full siblings share approximately 50% of their DNA. In contrast, half-siblings can share 0 to 50% of their DNA from a single parent. And typically, half-siblings share approximately 25% of their DNA. While full siblings share 2 parents, half-siblings will only share 1 parent. For 2 full siblings at a given locus, there is a 0.5 chance that 1 allele will be shared, a 0.25 chance that no alleles will be shared, and a 0.25 chance that both alleles will be shared from both parents. For 2 half-siblings at a given locus, there's a 0.5 chance that 1 allele at a single locus will be shared, and a 0.5 chance that no alleles will be shared from a single parent. And while full siblings can inherit up to 2 alleles per locus, half-siblings can only inherit 0 or 1 allele per locus by descent from a common ancestor. For kinship testing involving an alleged parent and child, the parent is expected to transmit an obligate allele to the child. However, for siblings, no obligate allele is transmitted from one sibling to another. For this reason, the sharing of alleles between siblings can vary significantly and cannot be predicted. Some siblings may share a high number of alleles from their parents, while other siblings may share significantly less alleles. In this example, we have 3 full siblings shown who share the same mother and the same father. As we can see, sibling 1 and sibling 2 share 60% of their DNA. However, sibling 2 and sibling 3 only share 30% of their DNA. This is only one of the many possibilities involving levels of shared DNA between full siblings. As shown by this pedigree, full siblings can share 0 to 100% of their DNA, which varies from sibling to sibling. In this next example, we have two full siblings who share the same mother and the same father. In addition, we have an additional half-sibling who shares the same mother but has a different father from the other two children. As we can see, sibling 2 and sibling 3 share only 10% of their DNA. However, sibling 1 and sibling 3 share 30% of their DNA. This example shows how half-siblings can share 0 to 50% of their DNA from a single parent, but these levels vary among siblings and once again cannot be predicted. One important aspect to understand is that as the amount of shared DNA increases, the evidence supporting the biological relationship also increases. The evidence supporting the biological relationship is commonly expressed as a likelihood ratio value. Likelihood ratios are commonly utilized measures for assessing the relatedness between two individuals in kinship testing. In 2017 through 2018, the AABB, American Association of Blood Banks, released the 13th edition AABB standards for comparisons of full sibling and half-sibling likelihood ratios. These standards state that likelihood ratios greater than 10 shall be considered evidence supporting the tested relationship, while likelihood ratios between 0.1 and 10 shall be considered inconclusive for the tested relationship. Likelihood ratios less than 0.1 shall be considered genetic evidence not supporting the tested relationship. Additionally, before reporting an inconclusive result, the laboratory shall use a minimum test battery of at least 20 autosomal STR loci when testing. Next, we're just going to discuss a few studies conducted previously on kinship testing involving siblings. In our first study, von Wormschwark et al. Studied full siblings, half-siblings with different fathers, and unrelated individuals to establish background data for SibShip analyses in forensic casework and kinship testing. They determined that 15 to 20 STRs can reliably establish biological relatedness between alleged siblings. They also suggested that a cutoff level for full SibShip should be set above a likelihood ratio of 9, since they observed that a likelihood ratio above a value of 9 correctly identifies 92% of pairs of individuals as true full siblings. In a second study, Lee et al. Used a virtually simulated population to evaluate the effectiveness of SibShip testing involving trios of siblings with one putative sibling and two reference siblings, in comparison to duos of siblings with one putative sibling and one reference sibling. They found that analysis of trio SibShip testing involving a putative sibling and two reference siblings with a fixed number of STR loci exhibited a higher degree of sensitivity, specificity, and accuracy in sibling identification than analysis of duos involving one putative sibling and one reference sibling using the same loci. In an additional study, Xi et al. Explored the kinship results from different types of relatives, including parents and siblings, and found that a greater number of reference relatives provides greater accuracy in the identification of a biological relationship in question. By simulating the pedigrees for common reference scenarios using 13 STRs, it was observed that first-order relatives, such as parents and full siblings, provided the most success at identification of missing persons. It was also observed that distant relatives may not be useful in the identification of a biological relationship using only autosomal markers. However, the use of autosomal markers in combination with lineage markers, such as Y chromosome and mitochondrial DNA markers, can increase the likelihood ratio and successfully identify a putative relationship. Due to this massive variation among the amount of DNA shared between two siblings, this research investigates how the use of additional reference siblings affects the results of a kinship test, and whether kinship testing should be performed on more than 2 siblings whenever possible. Additionally, the effect of substituting half siblings for full siblings is examined in order to assess if less information is obtained using half siblings in a kinship test. Next, I'd like to discuss the materials and methods involved in this research project. And the first part of this research involved running a series of simulations. DNAView, a statistical software program created by Charles Brenner, was used to run kinship simulations. These kinship simulations generated a range of expected likelihood ratios and determined a representative likelihood ratio for each subship scenario. 1,000 simulations were run for each potential subship scenario. For full siblings, these subship scenarios included kinship testing using 1 full sibling reference, 2 full sibling references, 3 full sibling references, and 4 full sibling references. For half siblings, these scenarios included the use of 1 half sibling reference, 2 half sibling references, 3 half sibling references, and 4 half sibling references in a kinship test. Now this image is just a screenshot from DNAView, and this image shows the result from running 1,000 simulations for a scenario using 1 full sibling reference from the Caucasian population. And as we can see right here, we have the 1,000 simulations plus the Caucasian population here. And as you can see, the representative likelihood ratio was 2,400 from the 1,000 simulations, with a 1 standard deviation range from 2,000 to 2,700. For this scenario, the likelihood ratio involved observing the genetic profile under 2 competing hypotheses or scenarios. The first hypothesis states that child D is the full sibling of child C, and that they share the same 2 parents, Ma and Pa. While the alternative hypothesis states that child D is some random, unrelated individual in the population, which you can see by OM and OF, which means other mother and other father. So the first hypothesis states that the alleged relative is the true relative, while the second hypothesis assumes unrelatedness. The second part of this research project involved using 415 known DNA samples sourced from AGTC in Denver, Colorado. These samples were provided by the Department of Forensic Science at the George Washington University. For these known samples, the parental relationships were previously verified through genetic testing. Half-siblings were defined by cases in which multiple non-excluded mothers occurred, while full siblings were defined in non-excluded multiple child cases. The samples were collected from 96 total families from European, Hispanic, African American, and Asian populations. Each ethnic group contained 24 families. The previously extracted DNA samples were quantified using the Quantifiler Duo DNA quantification kit. The samples were then diluted to 0.5 nanograms per microliter and were then amplified using the Global Filer and Verifiler Direct PCR amplification kit. The samples were then analyzed using an Applied Biosystems 3130 genetic analyzer and GeneMapper IDX software version 1.4. DNAView was also used to calculate the likelihood ratios for the samples of biological full siblings and half siblings within the families containing multiple children. A total of 241 subship scenarios were examined. For full siblings, 193 subship cases were calculated, while 48 subship cases were calculated for half siblings. These calculations used 20 autosomal STR loci from the Global Filer kit. and the samples from each of the population groups, which are Asian, European, African American, and Hispanic, were calculated separately using the appropriate population statistics. For these SIBSHIP cases, the parental genotypes in each case were ignored. The likelihood ratios for each SIBSHIP scenario were calculated in DNAView using only the STR genotypes of the siblings. Using these likelihood ratio values from the calculations, the strength of the biological relationship was determined. By comparing these likelihood ratio calculations obtained from the different SIBSHIP scenarios, it was determined, first, if the biological relationship is strengthened when using an increased number of reference siblings in the kinship test, and also if there's a significant difference in the strength of the biological relationship when using half-siblings instead of full siblings in the kinship test. Now first I'd like to discuss my results from my simulations, and this particular graph shows the results from the simulations performed for the SIBSHIP scenarios involving full siblings. The number of reference siblings is on the x-axis, and the representative likelihood ratio is on the y-axis. Now, when one full sibling reference is used in the kinship test, the representative likelihood ratio is 2,400, with a one standard deviation range from 2,000 to 2,700. When two full sibling references are used, the likelihood ratio is 800,000, with a one standard deviation range from 690,000 to 920,000. When three full sibling references are used in the kinship test, the likelihood ratio is 2.70 times 10 to the 7th, with a one standard deviation range from 2.3 times 10 to the 7th to 3.1 times 10 to the 7th. Lastly, when four full sibling references are used in the kinship test, the likelihood ratio is 3.90 times 10 to the 8th, with a one standard deviation range from 3.4 times 10 to the 8th to 4.4 times 10 to the 8th. Now, as we can see in this graph, there is a linear relationship between the number of reference siblings used in the kinship test and the representative likelihood ratio from the 1,000 simulation. So, as the number of reference siblings increases, the representative likelihood ratio will also subsequently increase. Now, this graph shows the results from the simulations performed for the SIBSHIP scenarios involving half-siblings. The number of reference siblings is on the x-axis again, while the representative likelihood ratio from the 1,000 simulations for each SIBSHIP scenario is on the y-axis. Once again, with one half-sibling reference used in the kinship test, the representative likelihood ratio is 7.47, with one standard deviation range from 7 to 7.98. When two half-sibling references are used, the representative likelihood ratio is 28.4, with a one standard deviation range from 26.2 to 30.9. When three half-sibling references are used, the representative likelihood ratio is 64.6, with a one standard deviation range from 59.7 to 69.9. And lastly, when four half-sibling references are used, the representative likelihood ratio is 108, with a standard deviation range from 100 to 117. Now, as we can see in this graph, this also exhibits a linear relationship between the number of reference siblings used in the kinship test and the representative likelihood ratio obtained from the simulation. Once again, the simulation shows that the likelihood ratio increases as an increased number of reference siblings are used in the kinship test. Now I'd like to show you the results from the samples that we used for the full siblings from the families containing multiple children among all four populations. As we can see again, the number of reference siblings is on the x-axis, while the likelihood ratio from each case is on the y-axis. The range of likelihood ratios from the samples of full siblings range from 0.659 using one reference sibling all the way to 1.34 times 10 to the 20th using four reference siblings. The results follow the model from the simulation and show that the likelihood ratio increases as the number of reference siblings used in the kinship test increases. However, it is clear that the value of the likelihood ratio plateaus with the use of four reference siblings, as we can see right here. And as we can see, there is no significant increase in the value of the likelihood ratio at this point. Now this table shows the median likelihood ratio for each SIBSHIP scenario involving full siblings. For a scenario in which one full sibling reference is used in the kinship test, the median likelihood ratio is 2.17 times 10 to the 6th. When two full sibling references are used, the median likelihood ratio is 2.12 times 10 to the 10th. When three full sibling references are used, the median likelihood ratio is 6.50 times 10 to the 12th. And when four full sibling references are used, the median likelihood ratio is 3.80 times 10 to the 13th. Now this table shows the ranges of likelihood ratios obtained for each SIBSHIP scenario involving full siblings. When using one full sibling reference in the kinship test, the highest likelihood ratio observed was 1.08 times 10 to the 19th, and the lowest likelihood ratio observed was 0.659. When using two full sibling references in the kinship test, the highest likelihood ratio observed was 1.45 times 10 to the 18th, and the lowest likelihood ratio observed was 12.6. When using three full sibling references in the kinship test, the highest likelihood ratio observed was 1.26 times 10 to the 20th, and the lowest likelihood ratio observed was 13. When using four full sibling references in the kinship test, the highest likelihood ratio observed was 1.34 times 10 to the 20th, and the lowest likelihood ratio observed was 8,090. This table shows that the likelihood ratios increase when the number of full sibling references increases. Additionally, it shows that the lowest likelihood ratio observed steadily increases. With the use of two full sibling references, all cases exhibited results with a likelihood ratio greater than 10. Now I'd like to show you the results from the samples of half-siblings from the families containing multiple children among all four populations. The number of siblings, the number of reference siblings, is on the x-axis, while the likelihood ratio calculated from each case is on the y-axis. The range of likelihood ratios from the samples of half-siblings ranges from 0.380 using one reference sibling to 4.06 times 10 to the 7th using three reference siblings. The results follow the model from the simulation and show that as the likelihood ratio increases, the number of reference siblings increases as well. And now this table is the results of the half-sibling samples, and this shows the median likelihood ratio for each SIBSHIP scenario involving half-siblings. So for a scenario in which one half-sibling reference is used in the kinship test, the median likelihood ratio is 112.5. When two half-sibling references are used, the median likelihood ratio is 6.32 times 10 to the 3rd. And when three half-sibling references are used, the median likelihood ratio is 3.08 times 10 to the 7th. Now this table shows the ranges of likelihood ratios obtained for each SIBSHIP scenario involving half-siblings. When using one half-sibling reference in the kinship test, The highest likelihood ratio observed was 17,900, and the lowest likelihood ratio observed was 0.380. When using two half-sibling references in the kinship test, the highest likelihood ratio observed was 9.85 times 10 to the 6th, and the lowest likelihood ratio observed was 5.62. When using three half-sibling references in the kinship test, the highest likelihood ratio observed was 4.06 times 10 to the 7th, and the lowest likelihood ratio observed was 2.09 times 10 to the 7th. This table shows that the likelihood ratios increase when the number of half-sibling references increases. Additionally, it shows that the highest likelihood ratio observed and the lowest likelihood ratio observed steadily increase with a greater number of half-sibling references used in the kinship test. Additionally, this table shows that with the use of three half-sibling references, all cases exhibited results with a likelihood ratio greater than 10. The results agree with the results from the simulations involving half-siblings. The likelihood ratio increases as more reference siblings are used in the kinship test. Now I'd also like to discuss our results. And after observing these results, we can see that the likelihood ratio increases when using an increased number of full sibling and half-sibling references in the kinship test. Since there is a greater amount of genetic information available when using multiple siblings, the likelihood ratio subsequently increases. This increase in the likelihood ratio provides greater support for the biological relationship in question. We can also see from the results that the likelihood ratios steadily increased when utilizing an additional reference sibling for full siblings until 4 reference siblings were employed in the kinship test. At this point, the likelihood ratio values plateaued, and there was no significant increase in the value of the likelihood ratio. As we can also see, the likelihood ratio decreases when using half-siblings instead of full siblings for calculations in a kinship test. This makes sense since half-siblings share less DNA than full siblings and from only one parent, so less genetic information is available in the kinship test. Now I'd further like to discuss the results and the findings from the full siblings. Only 3 cases out of 193 cases using full sibling references exhibited a likelihood ratio value below 10. And these 3 cases yielded inconclusive results with likelihood ratios ranging between 0.1 and 10. The remainder of the samples using full sibling references yielded a likelihood ratio value above 10. For half-siblings, a total of 5 cases out of 48 cases using half-sibling references exhibited a likelihood ratio value below 10. The 5 cases yielded inconclusive results and also exhibited likelihood ratio values ranging between 0.1 and 10. The remainder of the samples using half-sibling references yielded a likelihood ratio value above 10. Now, to explain the range of likelihood ratios among samples with the same number of siblings, we can assume that samples with a higher likelihood ratio share a high number of alleles, or they may share rare alleles in the population, while samples with a lower likelihood ratio may share less alleles, or they may share more common alleles in the population. However, there is no way to predict allele sharing in advance of testing. Now, the use of an increased number of reference siblings when necessary is beneficial since there is more genetic information available to establish the biological relationship. While there are costs associated with testing an increased number of siblings in DNA kinship testing, more genetic information is obtained and allows for stronger support for the biological relationship in question. However, while there are benefits to using a higher number of siblings, there are associated costs. For example, one of the major costs is the accessibility to multiple geographically distant family members, which may be very difficult for many individuals. Additionally, after a survey of labs that conduct relationship testing, the approximate cost of a legal kinship DNA test is $210 per person. Therefore, for a kinship testing involving one putative sibling and one reference sibling, the price doubles to $420. When two reference siblings and one putative sibling are used in the kinship test, the price is $630. When three reference siblings and one putative sibling are used in the kinship test, the price becomes $840. And a kinship testing involving four reference siblings and one putative sibling is over $1,000. So some of the conclusions that we obtained from these results, especially for full siblings, is that using the AABB standards, 20 STR loci is effective for full sibling cases. Over 95% of the time, the likelihood ratio was greater than 10. These results exhibited enough evidence to support the tested relationship with one full sibling reference. Less than 5% of the time, the results were inconclusive, but were resolved with the addition of one additional full sibling reference, for a total of 2 full sibling references. Additionally, any inconclusive results observed for full siblings were always resolved by testing an additional reference sibling in the kinship test. No samples resulted in the exclusion of the known true biological relationship. And as the distribution of shared alleles is a probabilistic phenomenon, the results indicate that a maximum of 3 full sibling references should resolve inconclusive cases if the siblings are in fact not excluded. The number of individuals sharing 0% of alleles will increase as the number of sibling pairs increases. Now I'd like to discuss some of the conclusions regarding half-siblings. Once again, using the AABB standards, 20 loci is effective for half-sibling cases. Approximately 90% of the half-sibling pairs have enough evidence to support the tested relationship with only one half-sibling reference. The remaining 10% were inconclusive, but were resolved with testing an additional 1 to 2 half-sibling references, for a total of 2 to 3 half-sibling references. Additionally, inconclusive results could be resolved by testing additional biological half-sibling references. And once again, no samples resulted in the exclusion of a real relationship. Now, in cases involving full siblings, any instances where inconclusive results are obtained is small. Since recollection may be difficult and time-consuming, it may be wise to collect samples on as many full siblings and half-siblings as possible. In regards to full siblings, up to 3 full sibling references are recommended. However, it is recommended to only test them as needed in situations where inconclusive results are obtained. This collection of multiple samples is relatively inexpensive in comparison to DNA testing of multiple samples. It is also more beneficial to test full siblings instead of half-siblings whenever possible. So as a conclusion, some recommendations from this research is that despite the cost of collection, it is recommended to collect samples on multiple full siblings and half-siblings when performing kinship testing with siblings. It is also recommended that when performing kinship testing, it is beneficial to test multiple reference siblings when deemed necessary for situations in which inconclusive results have been obtained. Additionally, when performing kinship testing with full siblings, it is recommended to use a maximum of 3 full sibling references. The addition of more siblings after that point may not be cost-effective. It is also recommended to utilize full siblings instead of half-siblings in a kinship test when possible. The practice of using full siblings and additional reference siblings provides a greater deal of genetic information in the kinship test and can lead to improved kinship results when inconclusive results are initially obtained. I'd like to acknowledge my family, my friends, my professors, and fellow colleagues for their support while I conducted this research. I'd like to acknowledge Charles Brenner for his assistance with DNA View in this research project. And I'd also like to acknowledge Chris Miles of the Department of Homeland Security Science and Technology Directorate for funding this research project. I'd like to also acknowledge Amanda Sozer and Brianne Knight for their guidance and assistance with this research project. And I've provided my references on these slides. And I'd now like to open the floor, the virtual room, for any potential questions that our audience might have.
All right, thank you so much, Brandy. We do have quite a few questions that came in while you were talking. Before we do jump into that, if all of our participants will look down at the bottom of your screen, you will see Brandy's contact email there. She has agreed to take questions directly from our audience, so for any reason your questions do not get answered or you have any follow-up questions, please make sure to take that down. That way you can contact her directly. So our first question that came in is from Maria. She's asking, were these studies run through different populations or were they just run through one, meaning the different allele frequencies?
So for each specific population, we used one allele frequency database when we were conducting for each ethnic group. So for all of our samples from the Asian population, we used a single Asian database of allele frequencies. Similarly with the Hispanic population and the African American population and the Caucasian population.
All right, great. Our next question is asking, did you also consider if the siblings were of the same or different sex? They were wondering if that would make a difference in the percentage of the match.
That is actually a very interesting question. These families contained a range of, full siblings that were two brothers or full siblings that were two sisters, half siblings that were brothers and sisters. And we never actually really looked into the effects of the sex of the samples. But that would be a very interesting topic to look towards for future studies.
All right. Our next question is from Eric O'Neill. He's asking, what was the hypothesis for the half-sibling analysis?
Oh, so the hypothesis for the half-sibling analysis. So as we can see, if I could actually refer back to one of my slides, if that's okay, Josh, just to make it a little bit easier for the audience to see.
Not a problem. That should be
I'd like to refer. Wonderful. Thank you. Just give me one moment to go back to the slide. Okay, so here we have the DNA View simulation, and as you can see, this was the hypothesis that we had for full siblings. Now for half siblings, what we did was we had child C is a child of Ma and Pa, child D is the child of Ma and other father, over child is the child of Ma and Pa, over child D is the child of the other mother and the other father. So basically the hypothesis was that child D is the half-sibling of child C, and that child D has a different father or different mother. We definitely considered this when we were doing each of the different hypotheses for each of the different cases. In cases where the two siblings had a different mother, we would definitely change that within the hypothesis, while the alternative hypothesis would be that child D is completely unrelated to child C. So I hope that helps answer that question.
All right. Our next question is from Megan Schaefer. She's asking, are the half-sibling references all half-siblings to each other or only half-siblings to the child in question?
So they are half-siblings to the child in question. We wanted to make sure that the sibling that we were testing was a true half-sibling of any references.
All right. Next question that came in was asking why the plateau was at 4 siblings.
Now, that was actually a really interesting finding when we started graphing the results. And from what I can assume is that when adding an additional reference sibling, when you get up to 4 reference siblings, at least in full siblings, there's just really no increase because you're kind of reaching that threshold where you have plenty of genetic evidence and it's just you're not seeing a major increase in the likelihood ratio. We definitely did see very minimal increases in the likelihood ratio, but not significant enough to really recommend that over 3 full sibling references should be used.
Okay. The next question that came in was from Jean-Francois. Asking, is the average IBD of the population taken into consideration somewhere in the likelihood calculations?
Yes, as far as I know, DNA View includes all of that information when you are conducting these analyses.
Okay. The next question we have is from Sonia. She's asking, it would be interesting to see which identifier kit, 15 STR instead of 20, if the plateau is still at 3 siblings. And they were asking if you had done this comparison.
I did not do this comparison for this specific research project. I only looked at the results from the global filer kit. But definitely for future studies, it would be interesting to see if this trend is observed amongst different kits and also just among different locations in general.
All right. Next question is from Joseph Warren. He's asking, in instances where no additional reference samples are available, would you recommend additional loci? And if so, how many? And what about the use of lineage-based markers when applicable? And he also said, thank you, you gave a great presentation.
Well, thank you, Joseph. If we do not have any more siblings, then it would be beneficial to try to test additional locations and additional loci. And as far as lineage markers, I think that that would definitely be beneficial, especially from past studies that have looked at the testing of lineage markers, and they've noted that the likelihood ratio does increase when incorporating lineage markers.
Okay, we have a two-parter from Jaslyn Salvador.
Okay.
The first question is, she might have missed this, she missed the very intro. Is LR less than 10 considered as an inconclusive? And also, did you include theta, population substructure correction, in the LR calculation?
Wonderful. Well, let me go back to one of the slides since she missed the introduction. So basically, I determined, if the results were inconclusive or whether the results did not support the tested relationship or the results did support the tested relationship based upon the 13th edition AABB standards. And so for likelihood ratios between 0.1 and 10, that is considered inconclusive for the relationship. And any likelihood ratios less than 0.1 are considered genetic evidence not supporting the tested relationship. And in regards to the second question, we did incorporate beta into the calculations.
All right. Next question is from Catherine Stevens. She's asking, would using a higher number of STRs help increase the likelihood ratios?
I definitely think that increasing the number of loci and increasing the number of STRs will increase the likelihood ratios. However, we are really only kind of looking at being able to establish a biological relationship in question. And so sometimes it might not be necessary to increase the number of STRs simply because we've established a biological relationship already. But I definitely think increasing the number of STRs will increase the likelihood ratio.
All right, great. Next question is from Zach Gaskin. He's asking, did you have concerns with assuming that a reference sibling is a true sibling? Some simply may not know the truth.
Well, that's an excellent question. For this particular study, we already had the parents for all of the siblings, and these children were determined previously that they were the children of the parents, and so they were already known siblings from the start. So we definitely had a really great advantage starting the study, knowing that we were working with true known siblings that were determined to be siblings genetically previously to this study.
All right. Next question is from Christina Nash. She's asking, wouldn't we expect the plateau to happen higher, meaning more siblings would be needed since less loci were tested?
For the results of this study, we did see that that plateau for full siblings occurred at around 4 full reference siblings. However, I would definitely recommend for future studies that more siblings are tested to really see how that plateau occurs. And for the purposes of this study, we only had up to 4 reference siblings to work with within the families we had. But if possible, I would definitely recommend for future studies to see if that plateau still occurs at 5 reference siblings and using 6 reference siblings. And I'd also definitely recommend for future studies to see if for half siblings as well, if that plateau also occurs at around 4 reference siblings, or if the likelihood ratio value will just continually increase. Unfortunately, with this particular research project, for the 96 families we had, we only had up to 4 full reference siblings to work with and 3 half-sibling references to work with.
All right. Our next question is from Kevin Greeley. He's asking, did the testing population include any multiracial half-siblings? And are there any challenges with comparing multiracial half-siblings?
That is a very interesting question. For these specific populations, we only had African American, Hispanic, Asian, and Caucasian. And from my knowledge, these half-siblings all were within the same population. But it would definitely be an interesting topic to explore further to see the effects of using multiracial half-siblings and just the consequences of the different databases that are being used for each specific sibling.
All right. Next question we have is from, it's a follow-up from Jaslyn. She's asking, what is the value of the theta you used? Was it 0.01?
The value of theta was included in the DNA view calculations, and I will definitely have to double check on that, but I believe it was 0.01. But I can follow up with you later at a later time and give you a definitive answer on the value.
All right. The last question we have right now is from Miriam. She's asking, did you look into the effect of mixing full and half reference siblings?
That is an excellent question, Miriam. right now I am working on a publication for this research, and in that publication I definitely intend to look into that topic further. Just for the purposes of the presentation, I wanted to keep it full siblings and half siblings, but while I was conducting my calculations, I definitely saw some results when I was using full siblings and half siblings together when having one putative sibling and one half sibling and one full sibling. So definitely in my publication I will address that.
All right. Ed O'Neill or Eric O'Neill had a question. Were your distributions approximately normal?
Yes, our distributions were approximately normal.
All right. Kevin Greeley has another question. He's asking, are there any indicators of whether a half-sibling shares a common father versus a common mother with the reference sibling?
From what I saw, the results were definitely very similar when the half-sibling shares a common father versus when the half-siblings share a common mother. There weren't any significant differences in the values of the likelihood ratios that I obtained for that. That is an excellent question, though.
All right, we've got time for just another question or two. Jaslyn wanted to make sure that you knew that you gave a great presentation. The next question is
Thank you,
from
Jaslyn.
Zach Gaskin. What percentage of sibling cases do you estimate will have an additional sibling to utilize?
Well, in one of my conclusion slides, just from the cases that we examined for specifically half siblings, we saw that approximately 90% of the cases were actually able to be concluded to be a true relationship, and then the remaining 10% were inconclusive. So typically, just from our sample set, we saw that 90% of the half-sibling pairs had enough information, genetic evidence, to support the relationship with just using one half-sibling reference. And the remaining 10% were resolved with the addition of one to two half-sibling references, for a total of 2 to 3 half-sibling references. So from what I saw from my results, a majority of the half-sibling pairs were resolved with the addition of just one half-sibling, so for 2 half-sibling references total, and only a couple cases that I saw really required 2 to 3 half-sibling references total.
All right, great. In the interest of time, we are going to go ahead and move into our closing, but before we do, we always want to give our presenter the floor at the end. So we'd like to know what kind of additional research could have been conducted, and also where your research is going in the future.
Great. And for the future, I definitely recommend looking into the testing of additional reference siblings. For full siblings, I definitely recommend looking into testing 5 reference siblings, 6 reference siblings. And especially with half siblings, I definitely recommend looking into the testing of additional reference siblings past 3 to 4. Just so that we can really see if these plateaus that we noticed really occurred, as they would with the full siblings.
All right, thank you so much, Brandy, for your presentation today. Before we get into our closing, I would like to hand the floor over quickly to Chris Miles.
Chris Miles from DHS Science and Technology. I just wanted to quickly say thank you to Brandy for this test for this research. You know, DNA is such a critical capability for DHS in a number of areas, and we really appreciate this research. I also want to extend a thank you to Dr. Moses Shanfield and Dr. Daniel Podini at George Washington University, and Dr. Sozer and Brandy Knight at SNA for their help with this. Thank you for everyone that participated in this research. It'll be very useful for us.
All right, thank you very much, Mr. Miles. With that, we are going to go ahead and close out today's webinar for today. Before we do go, you will notice in the bottom left-hand corner of your screen, there is a file share pod with the PDF version of today's slide deck. So please make sure you do download that before you leave today. Simply click on the title of the document, and then the download files button below will become highlighted for you and allow you to download that directly from your from the room today. Also, we do have 2 other registrations open for the DNA Kinship webinar series. You will see hyperlinks there on your screen for March 14th and March 21st. So please go ahead and make sure to click on those links. They will open up new windows for you, and you can go ahead and register for those events today. Before you leave, we always put up our customer satisfaction survey for you to take. It's a very brief survey. Your feedback about our webinars is vital information that we do always use to make sure we are providing you with the best webinar experience, and also to adjust the content and also the way we disseminate the information out to you, our audience. So if you could please take a few moments to complete that survey, we would definitely greatly appreciate it. You will see Julian over there in the chat pod on your left-hand side putting some of our plugs in for our Forensic Center of Excellence websites, as well as social media, Twitter, Facebook, LinkedIn, as well as our podcast that we are currently putting out. Again, thank you so much to our subject matter expert, Brandy Iorio, and all of the cast and crew that made this webinar series possible. And thank you for our audience for joining us today. Without your presence, these webinars would not be possible. We hope everyone has a great rest of your afternoon, and we will see you on the next Kinship webinar in the series.